Hi, I'm making this video as a part of my homework for property and stochastic processes. This is homework 10 question 2. The question 2 asks us to define Whiteson stationary process. A stochastic process is a Whiteson stationary process if the mean is a constant and the autocorrelation of T1, T2 is autocorrelation of the difference, that is T1 minus T2, and the autocorrelation only depends on the variables T1 and T2. The examples for a Whiteson stationary process are Poisson's increment process, Poisson's impulse process, and random telegraph signals. We can say that if x of t is a SSS, which is a strict sense stationary, and expectation of x square of t exists, then x of t is a Whiteson stationary process. The second part of the question asks us to define independent increment process. X of t is an independent increment process if the property mass function p of x of ta minus tb being less than x1, and the x of tc minus td being less than x2 is equal to property of x of ta minus x of tb being less than x1 into probability of x of tc minus x of td being less than x2 for any non-overlapping intervals. The examples for independent increment process are Poisson process, random walk, and Wiener process. The third part of the question asks us to define Markov process. The process is said to be a Markov process if the past has no influence on the statistics of the future, considering the fact that the present is known. That is, for a Markov process, any probability mass function depends only on the current values which we know, and not on the past values and not on the future values. So probability of x of t1 is less than x1. That similarly, in probability of x of t2 is being t2, x of t3 being t3, and so on, x of tn being xn. Is equal to probability of x of t1 being less than x1, conditional on x of t2 being equal to x2. So it can be statistically determined if one knows its second order distribution function, that is f of x1, x2, and t1, t2. And the examples for such process is Poisson process, semi-random telegraph signal, and random walk and Wiener process. And the fourth part of the question asks us to define a normal process. A process x of t is said to be normal if the random variable x of t1, x of t2, and similarly x of tn are all jointly normal for any value of n and any value of t, that is for n for t1, t2 up to tn. That is nothing but f of fx of x1, x2 up to xn and t1, t2 up to tn is defined as is given by 1 by square root of 2 pi whole to the power of n, square root of determinant of c into e to the power of minus half x minus n into t by c inverse x minus n. The fifth part of the question asks us to define strict and stationary. It is said to be any process is said to be SSS if its statistics is not affected by a shift in the time axis. That is, x of t and x of t plus epsilon both have the same statistics, where epsilon is the time shift that we are considering. So any process x of t is SSS if for fx of x1, x2 up to xn, comma t1, t2 up to tn is equal to fx of x1, x2 up to xn, which will be same, but the time is shifted to t1 plus t, t2 plus t, and similarly up to tn plus epsilon. So any sequence of independent identical distributed random variable is a SSS. So sixth part of the question asks us to define white noise. So for white noise, we can write the autocorrelation of t1, t2, and q of t1 is equal to delta of t1 minus t2. Then v of t is defined as white noise. So white noise is a process such that the values at different times, that is x of t1 and x of ti and tj, are nearly independent, and actually they are uncorrelated. So q of t1 into delta of t1 minus t2 is called as the average intensity. The seventh part of the question asks us to define mean ergodic process. A stochastic process is said to be an ergodic process if all the statistics can be determined by just one sample. That is, x of t is said to be mean ergodic if e of x of t is equal to limit where t tends to 0, 1 by 2t into integration of minus t to t x of t into dt.